So a couple of more reactions left, and we're going to start with the first one in this video, and then the next video, which will probably be the final, we'll look at our second. And in this video, we're going to talk about something that we call Wolff Kishner. All right, so let me spell that out. Wolffkishner in a tree. You remember that rhyme? You probably said it in elementary school. So-and-so, Kissing. Well, Wolff, Kishner. Wolff Kishner. That's the reaction that we're talking about. This reaction is a review. Who would have known? This reaction is actually a review of many different things that we have discussed at this point. So we're talking about type 2, C double bond O. And on one side is an R, and on the other side is either an R or an H because we're using an aldehyde or a ketone. So C double bond O, sandwiched, carbonyl, and this reaction is a carbonyl-based reaction. Okay, so what goes on here is that we can form a product. Who would have thought? And that product, well, this is what's going to happen to the product. Ignore that. That was a silly mistake. Here we go. And in the long run, before and after, that's how we're going to start this reaction, because I think it will help you quite a bit when we begin talking about this awful mechanism. We can take an aldehyde or a ketone and we can react it with a reagent. I'm not going to write down that reagent right now. And what happens is that we can take this reagent, add them together. Hopefully we don't kill ourselves when we do it. And then what we end up with, the product in the very end, is a that's it. That's all we do. We eliminate the oxygen, folks, and nothing goes on. No nucleophile. No extra group. Other than some hydrogens to make carbon happy because it just lost 2 bonds. So, of course, hydrogen's going to have to go in. But that's it. We get rid of the carbonyl. We don't have any extra functional groups that get added onto the molecule that we're going to have to deal with later. Maybe we won't want those groups. That's basically what Wolff Kishner does. This whole process has a term that we call, now bear with me, this is going to be complicated, Deoxygenation. What an awful complicated term. Deoxygenation means D, get rid of, oxygen. I'm going to get rid of the oxygen. Bing, bing. There we go. Bye-bye. Away it goes. Perfectly pleasy, very happy. So I am undergoing a reaction. The reaction is called deoxygenation. Deoxygenation is going to happen with a type 2 carbonyl other than an aldehyde or a ketone, one or the other. And the process of deoxygenation is going to be to destroy the carbonyl bond of the group. When that carbonyl bond of the group is destroyed, what we end up with at this point is a traditional kind of alkane type of molecule. No additional functional groups go onto the molecule. That is it, folks. Again, wrap it up. Nothing to see. That's all that goes on. So this is called deoxygenation. And the reagent that is used in order to get this done is something called hydrazine. And hydrazine is NH2NH2. We saw this in a previous video. That's why I said part of this is a review here. So NH2 and NH2, very similar to some of those like imine derivatives and stuff that we've talked about. Well, if this goes on and we have full-blown NH2, NH2 hydrazine, if we add some extra reagent, we can get this to turn around and produce this product for us. And what we need here as well is a little bit of base and maybe some water. And the water molecule sometimes isn't even written because we're generating water in the process. So sometimes people will only write OH that's there. We're making water through the process. Others like to write the water because they regard it as a second step, and that second step requires the water to go forward. So they want to make sure that water is actually present on the arrow just to say, hey, this is what goes on. So you get the picture. And folks, this is what we call the Wolff Kishner reaction. It's a deoxygenation that is driven by hydrazine and a little bit of base with some water if you want to add it in. All right, so here's the thing. Hydrazine is actually super toxic. It's going to kill you. So if I have a laboratory class and we're doing a Wolff Kishner reaction and we're doing hydrazine, then I hope that I don't kill everybody in the class. I hope that you don't kill everybody in the class when you do the reaction if you're not doing it the right way. So you can kind of understand the hazards that are associated with Wolff Kishner. However, Wolff Kishner is heavily used in the pharma industry. And the reason is because it makes pharmaceuticals. And it's also used in the environmental industry because it makes pesticides. These are precursors to make many drugs and many pesticides that we use on the consumer market. So that's why we often talk about Wolff Kishner. Again, if your point in taking this class is to go and work in a laboratory or with a laboratory company, this is where you're going to see this stuff. If your point is to go to pharmacy school or to medical school, or if it's go to nursing school to get a higher degree, then you probably don't really have to worry about Wolff Kishner. But we can't do those people an injustice if they do want to work in the lab. And these are the things that we have to talk about. All right? Okay, so I'm going to go through this mechanism, and I want you to follow with me just for a little bit, so that way you can understand how this process plays out. So here I'm going to take just a benzene ring because that's like module 2 stuff, right? I want to go through and I want to kind of tell you and remember, hey, benzene. All right, so here's a carbon and there's a double bond O, and then here is a CH3 molecule or group. All right, so it looks like I'm starting with a ketone here, right? And this ketone, perfectly okay, it's a type 2 carbonyl. And I can react this ketone with NH2NH2, which is hydrazine. And a reaction can go forward. So this reaction, very similar to the imine derivative reactions that we've talked about. Again, it's a review. That's all that this is. So in those reactions, if you go back and take a look at your notes, what you're going to see is the ring is going to be untouched. That carbon is there, double bond O. This methyl group is there. And we have reacted this with NH2NH2. And what we said in the imine derivative section of your notes is that we that oxygen away, and this nitrogen goes on and it brings its buddies to the club. So here's the buddy, NH2. So this is what we form in the very beginning. And during that time, this is where we stopped the reaction and we said, this is the product. And then later on, I said, well, this is kind of an imine product, a C double bond N. And that C double bond N I followed up with, and I said, well, those are not very stable, you know, so we can kind of react those with something else and go a little bit further with them. And this is what we're going to do here. But in those previous steps, we just really stuck with H2 and palladium. I mean, that's really all that we did. We broke the double bond and hydrogen went on one side and hydrogen went on to the other. So what we're doing here is something a little different because we have added base, not H2 and palladium. And this is where this takes a different type of turn. So this base is something as simple as OH minus. It can come from anywhere, folks. Any base source would work. Sodium hydroxide, potassium hydroxide. I don't really care. It's an OH. So this base, what's the purpose of the base? Well, the purpose of the base is to go in and accept a proton if it can find one. And we have one. Look, this nitrogen here, this has an H2. All right, so what I'm going to do, I'm going to erase this H2 and I'm going to draw it a different way. I'm just going to put a hydrogen here and a hydrogen there. There's an NH2 piece. Well, the base comes in, all bold, confident of itself. I'm a base and I'm here to take the proton. Give me a proton. I mean, that's basically what it's saying. So this base sees this proton and it says, hey, nitrogen, you want to give me your proton? I'm sure you can maybe find your way and kind of do something in the molecule to make yourself happy if you do that. And the nitrogen says, you know, OH, I think I'll take you up on your offer. You know, there's a lot going for me here. And I can rearrange myself and I can maybe make this work out into my favor. But in order to do this, yeah, you're going to have to take the proton away from me. So this OH pulls that hydrogen off. And that goes and makes HOH, which is water. All right, so what we have left is a benzene ring with a carbon, a CH3, a double bond N, bonded to an N, and now we have just one hydrogen that is there, and that is it. Now at this point, this nitrogen is not happy, folks, because there's two bonds. We've always said nitrogen likes three. So this needs an extra bond somewhere. And look at what has happened. Nitrogen knew it. Nitrogen planned for it. It was almost conniving in a way. 2 steps ahead. So when the OH pulls the hydrogen off from that nitrogen group, this forms a negative piece. And back in Chemistry 251, we discussed the concept of delocalization, didn't we? We had a couple of different roles, maybe 4, with delocalization. And one of those was electrons move to pi set. You remember that. Double bond moves to a double bond. A double bond moves to a positive. Pi electrons move to pi electrons. And folks, that's what we have here. So now that the hydrogen is gone, this nitrogen sees an opportunity. And this nitrogen says, hey, I've got these electrons. So nitrogen, I'm pretty. You're pretty. And why don't we just go hang out with our pretty selves? And that's about it. So you want to kick that carbon loose? You want to get rid of that carbon and just come and hang out with the pretty people? I mean, it's kind of like a sorority or a frat house, if that's kind of their attitude, right? You got to be in the clique. Well, not all sorority or frat houses are like that, but some of them are. So this nitrogen takes the electrons and it puts it in between those two nitrogens. And when that happens, nitrogen says, okay, nitrogen number 2, I see where you're going with this. So I'm going to take one of these bonds and I'm going to shove it to that carbon. And I'm going to let carbon just handle it. Because I think we could make this out. I like hanging out with pretty people because I'm pretty too. Okay, so this nitrogen starts to form a stronger bond with the other one. Now keep in mind, we have only added hydrazine and base. That is it. That's all that we've done. All right, so now what goes on? is that this ring is here. That carbon is still there. This methyl group is still here. And now we have this single bond to a nitrogen. This has shoved those electrons in between the two ends, forming a double bond here. And that still has the hydrogen on it. That's all that's happened. Electron set has moved in, forming a double bond. And nitrogen says, I can't have that many bonds, so I'm going to take this free set and I'm going to shove them over to carbon. Well, carbon now has a free set of electrons, so this is full-blown negative at this point. You can kind of imagine carbon's not very happy with this. But that's okay. Because look at what we made up here in the top right-hand corner. Water! So this water molecule, still around, still swimming, being nosy, looking at what's going on. That way it can call its best friend up and say, you would not imagine what these two nitrogens just did. This nitrogen called this other nitrogen up and said, oh my gosh, we're both pretty. Why don't we just hang out together? I saw it all happen right in front of me. So the buddy that it calls is this carbon. And the reason is because it sees that carbon in distress. It sees that that carbon is negative at this point. And that negative piece and this positive piece, as you can imagine, will have an association with each other. So this carbon goes up and it pulls that hydrogen off, and that shoves these electrons back to the OH group, making it regenerate the OH yet again. All right, so what we have now at this moment is a ring. There's a carbon here. That carbon has just gained a proton from the water, so that's why we draw the extra hydrogen. Still has that methyl group. Nothing's happened to it. Nothing's happened to the ring. It's all been about the carbonyl. This is still attached to the nitrogen. That still has that double bond. That still has that nitrogen and the hydrogen on it. Now, at this point, you might look at this and say, hey, everybody's happy, so this is our product, right? But this is not the product that we predicted in the very beginning in that general template that I showed you. Just the straightforward, here's the reagent, here's a product. Something else happens, and this is why. In the previous step, we generated some OH minus, and that OH minus is still there now. This OH minus is going to do what OH minus always does. And this OH minus is going to look for a proton that it was just robbed of. Well, it's going to look for something that can give a proton away. And it finds it. I told you nitrogen was 2 steps ahead. It planned all of this conniving and scheming little thing. So the OH group comes in and pulls this hydrogen off. Beep, beep, bye-bye. And it generates water again. Just like it did the very first time. The nitrogen is okay with that. Because what happens is that the bond between the nitrogen and the hydrogen will move those electrons to the nitrogen, giving that nitrogen a set of electrons, and that actually just goes ahead and shares it between the two pretty nitrogens, because that's what all of this was about. So when that happens, that nitrogen, too many bonds, the very first one, it's going to have 3 over here to the right, and it has a 4th to the left. So it takes those electrons and it just goes ahead and shoves them on over. Shoves them on over. And it says, carbon, you get those set too. So what we have is a ring that has a CH on it, that has a CH3 on it. These electrons have just been shoved to carbon again. So it reforms that negative. Carbon still can't get rid of that negative. And this, in the meantime, has formed N triple bond N. And folks, this is just nitrogen gas. That's all that this is. Very, very stable. Nitrogen loves this. Because one of the rules of general chemistry was diatomics. Do you remember those diatomics? I called them lucky sevens. That's because they started at number 7. They made a 7 on the periodic chart, and it was N2, O2, F2, Cl2, Br2, I2, and then H2 was kind of the oddball that was over on the left. So it starts at number 7. It makes a 7 on the periodic chart, and there's 7 of them. That's why I call them the lucky sevens. So this is very, very stable. Nitrogen loves to be N2. It's the diatomic version of it. Well, carbon's not quite happy. We need to satisfy that carbon. It's got this negative piece again. That's okay. We just generated some water from this previous step. Water is going to be here again to save the day, and that negative carbon will go in and pull a hydrogen from the water molecule all over. And finally, what we end up with is a benzene ring with a carbon that now has 2 hydrogens on it, not 1, and a CH3. So we have destroyed the double bond O using hydrazine and base, and that double bond O does not get replaced with anything other than just simple O hydrogens. And that's all that it takes. And this is what we call the Wolff Kishner reduction. The ketone reacts with hydrazine to form a hydrazone. That's the proper term for that. The hydroxide comes in and it removes a proton from the amine source, and the negative charge begins to delocalize onto the carbon, and then it will go through and repeat this process all over again with another round of water and OH. And it does it automatically. So round number 1 goes through, round number 2 goes through, double bond gets destroyed, and then no group goes on in its place. All right, so with that said, here's your mechanism for that reaction. Now I'm going to do some cleanup work. I'm going to show you how easy Wolff Kishner is. So forget about the mechanism at this point. Let's say that they give me an example problem, and it says, use a Wolff Kishner to predict the product of the following reaction. Okay, well, not a problem. This is no big deal. I'll show you how easy Wolff Kishner is supposed to be. All right, so there we go. There's my reagent. I've added hydrazine and some OH. I don't need to do the mechanism work every time. Mechanism is only there to help me explain why the reaction happens. That's all that it does. So I'll redraw the reagent like I always do. I'll do that first. There we go. CH3. Hydrazine, OH, Wolff Kishner. This is what happens. Beep, 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 beep. Double bond O goes away. And what we do, we put 2 hydrogens there instead. That's all there is to it. Don't make it more complicated than what it should be. This is all there is to it. Get rid of the double bond O. It does not get replaced with anything other than just some hydrogens. And that's it, folks. That's all that we have. So if I wanted you to go through and name the product, we can do this. This is a benzene ring, and this is an ethyl group on the benzene ring. So we can call this ethyl benzene. And there is a review of the second module of the semester that has now been wrapped into one of the last ones of the semester. Folks, look at this. That's the beauty again of organic. I keep saying it because it all connects together. That's the problem with organic. People do not connect the dots. All of these reactions tell the same story. All of these molecules tell the same story. It's about opposites. It's about attraction. It's about greediness. It's about bar life. It's about relationships. Folks, that's all there is to it. That's all that there ever has been to it, ever since day 1 in Organic 1. They're just different ways that it happens. Just like there's different couples that are out there. Some put up with more things than others do. Some have no patience. Some are attracted to the pretty ones. Some are attracted to the ugly ones. Some don't really care as long as it's got something to do a bond with. Some is only attracted to itself in the form of N2. It's diatomic. It's perfectly okay with a twin just like its own. It's kind of weird and creepy, but that's the way it is. All right, so this is a wrap-up of the Wolff Kishner. That's all that you have to do. When you see things like this ketone that we've done in this example, you get rid of that double bond, you replace it with 2 hydrogens, and away you go, folks. You have just formed your product. It's as easy as that. And we call this deoxygenation. That's what this is all about. All right, so in the next reaction, in the next video, probably going to wrap it up, is going to be our second special type of reaction that we call a Wittig. W-I-T-T-I-G. A Wittig. So come back. We'll talk about Wittig together, and we'll make fun of the name together.